Okay, let's dive into this. Because what we've got here is a genuine scientific detective story. Seriously. We're on the hunt for a phantom signal, this tiny little fingerprint in the noise that scientific theory tells us has to exist. The only problem? Yeah, no one's ever been able to find it. So imagine this. What if you built the world's most sensitive metal detector? You proved it could find gold every single time, and then you take it to a place you know is a gold mine, and it just stays completely silent. That's the crazy paradox at the heart of our story today. The gold in our story, the thing we're looking for, is something called a Feigenbaum pole. So let's take a closer look at what that actually is. Now, this Feigenbaum pole isn't just a guess. It's not a maybe. Its existence is a mathematical certainty, something that was proven a long time ago. You can think of it like a specific, predictable note that theory says must be present in the song of a chaotic system. So for scientists, the question isn't, does it exist? The real question is, can our tools actually hear it? And, this wasn't the first time scientists went looking for it. A previous investigation searched for this exact pole, and they came up completely empty. But that failure left this huge, unanswered question just hanging in the air. Yeah, the big problem with that earlier search, it all came down to the equipment. Was their detector just not sensitive enough to find the signal, or was something else going on entirely? And this was the fundamental problem, right? That null result they got was totally ambiguous. It could mean the pole wasn't there, or it could just mean their detection method was blind to it. There was just no way to be sure. So the crucial point is this. The old method was missing what's called a reference recovery check. They never actually tested their tool on a sample where they knew the signal was present. It's kind of like trying to find a needle in a haystack without first checking if your magnet is even turned on. And this is where our story really kicks off. A new team of researchers decided they were going to solve that problem once and for all. They set out to build a totally foolproof testing protocol to perfectly calibrate their machinery. So they came up with this 4-step filter. G1 through G3 are basically just sanity checks, to make sure you're not seeing a fluke or some kind of error. But G4, that reference recovery step, that's the game changer. This was the piece that was missing from the last investigation. It's actually a pretty simple idea when you think about it. Before you go hunting for some lost treasure, you test your detector on a gold coin that you already have in your pocket. If it beeps, you know the machine works. If it doesn't, well, you know you can't trust any of its results, positive or negative. So they put their newly calibrated detector to the test. They created a synthetic data set, and then they artificially planted a Feigenbaum-like pole right inside it. This was the moment of truth for their new method. And would you look at this? In the Alien-Strength Sector, which is one of the 3 areas they were investigating, the test was a stunning success. Every single time they ran it, with all different settings, they found the pole they had planted right where it was supposed to be. I mean, the researchers themselves couldn't have been clearer. I'm just going to read this directly from their paper. The machinery robustly recovers the designed pole, confirming it can detect a singularity when it is present. The magnet was on, the detector was working perfectly. So the stage is set. They've got a tool they can trust completely. They've proven it can find the gold. So now all that's left is to point it at the real-world data from the Feigenbaum cascade and see what it finds. All right, this is the climax of our detective story. After all that work, all that careful calibration, they finally analyzed the real data from 3 different sectors, all places where theory says that poles should absolutely be, and they found absolutely nothing. Not a single, stable Feigenbaum pole. The final count across all of their extensive searches was a perfect and perfectly shocking 0. And this wasn't a limited search either. They looked in 3 completely different ways, analyzing independent sets of data where the theory predicted the signal should appear, and all of them came up completely empty. Okay, but here's the crucial point, and this is why this matters so much in science. This wasn't a failure. A definitive no from a tool you know works is infinitely more valuable than some fuzzy maybe from one you can't trust. It proves the tool wasn't blind. The data itself is blind. And that opens up a much more fascinating puzzle. So if the pole is really there, but a perfect detector can't see it, what could possibly be going on? Let's look at the implications of this. Well, the paper proposes 2 main theories. The first one is basically that the signal is just too faint to see, like trying to read tiny text from way across a room. We just need to get closer, which in this case means collecting way more data. The other possibility is that the signal is being canceled out or masked, that it's there, but it's being hidden by other interfering signals in the data. It's hidden in plain sight. And this is how science really works, isn't it? What looks like a total dead end is actually a signpost pointing in a new, fascinating direction. The investigation has shifted from asking, can we see the pole, to the much more interesting question of why can't we see the pole? This result directly sets up the next whole phase of research. So we end not with a final answer, but with a much, much better question. We've solved the case of the potentially blind detector, only to uncover this much deeper mystery of the invisible pole. Is it just too weak to see for now, or is it being actively hidden by the very system that creates it? The hunt is far from over.